All right, so we're in research world again. Tell us who you are and what you're working on.
My name is Emre Kiciman, and I am working on large-scale systems management. So that means for internet services and large-scale systems, things with thousands of nodes, or tens of thousands or hundreds of thousands, we get into larger systems. How do you keep these things running? And really, the big challenge is that these systems are large enough, and they've been evolving over enough time that no one really knows what these systems are supposed to be doing or how they're supposed to be working. They're just in detail. You just have too much detail, too much stuff to fit into any one person's head.
Okay.
And so what I do is take advantage of the fact that we can grab a lot of data from these systems in terms of how they're behaving at a very, very low level. So, for example, you want to know what the CPU usage is on that machine over there, or whether that box is talking to that box. You can measure all that very easily. But this has nothing to do directly with the high-level questions you actually want to answer. Is the system running? Is it up? Is it reliable? And so my research is about taking all this low-level data that's easy to gather and finding ways to analyze it to answer the questions we care about at the high level. Issues in reliability and systems management, evolution of systems over time in terms of impact analysis of changes, things like that.
Now, do you do any work with remote debugging into a situation? So if you had a 1,000-node cluster that's doing some massive calculation to determine the density of the universe.
So for things like the parallel computing, and you're going in and there's some computation that it just dumps an error or something like that. That's the type of there's a class of tools to deal with that, where you basically do, like you said, remote debugging, where a guy comes in and will look at what that program is doing right when it crashed, and will try to understand the problem and fix it. The type of problem that I have been attacking are more like you have the same application running all over the place, billions of users either on people's client desktops with their web browsers and things like that, using an internet service, or thousands of copies of the program inside the system, and just every now and then it fails. And rather than making a person come in and try to understand what happened at that particular time, and then doing like the detective work of figuring out what's going on, can we take advantage of the fact that we have hundreds of thousands of copies of this, or millions of copies of this program running, to figure out, well, we have a bunch of programs over here that are working just fine, and a bunch of programs running over here that are crashing every now and then. What's the difference between the two? Is it the input to the program? Is it just some corner case in the code? Is it a particular type of hard drive that just crashes every now and then, and really it's some other type of problem, not the code? So can we take all this information, all these observations of both the good and the bad, and join them together to figure out what's causing it? And this is based on some work that's been going on in research now for a few years.
And now let me ask you this: what if the application is running on multiple platforms? That presents a challenge for you, doesn't it?
So there's the aspect of the instrumentation, which that ends up having to be more platform specific.
Okay.
Then there's the aspect of, once you have this data, it's come from a bunch of different platforms, how can you tell what's going on? And there, the fact that it's running on a different platform just ends up being one more clue as to what could be different between, if you're looking at, if you're looking at your website, you notice that, oh gosh, no one is coming over from this specific version of some browser somewhere, and everyone else seems to work just fine, then you might think that it's that browser's fault. It's something going on with your application on that browser specifically, and you can go dig into that. So it becomes one more feature to help you figure out and understand when things are working and when they aren't.
Excellent. So what do you call this research? Like, what did you study? How did you get into this?
So I'm relatively new here.
Okay.
I started at MSR about a year ago, and I got my PhD in computer science from Stanford University, and that's how I got to where I am right now. The general area that I'm working on is, I guess you'd call it, dependable computing or reliable computing or that type of thing. So right now I call it large-scale systems management, and then you're managing things for reliability or for low-cost operations and things like that.
Excellent. And so was your thesis or your dissertation related to this?
Yeah. So my dissertation work was on how you've got this big internet service, and you don't know. Not only do you not know how it's working, it turns out that if you talk to folks, in the details, you often don't even know what it's supposed to be doing. And so then the question is, how do I know whether it's doing it? Can I tell? Can I? So you got your operator running the system, kind of looking at a bunch of data about what's going on. So he sees, okay. I've got this much work over on this machine. I've got this much work being run on this machine. I'm getting this many people coming to my site every hour, every minute. Mm-hmm. And then from that, he's supposed to tell whether or not it's working. And people can do a pretty good job. If people stop coming to your site all of a sudden, it's probably a problem with your site.
Yeah.
But the question is that ends up being a lagging indicator, because people come to your site and let's say they're going to an e-commerce site or like a shopping site, right? Mm-hmm. They'll go browse your site, then they'll go and put things in their shopping cart, and they'll go to checkout. And let's say there's a problem in the checkout process. Mm-hmm. They spend 10 or 15 minutes in your site, and then they have a problem checking out, and then they leave. And so you'll notice that people aren't checking out anymore. But that's a lagging indicator. You won't notice it for 5-10 minutes after the problem first starts. Mm-hmm. And so that's a 5-10 minutes you could have had a head start on fixing the problem before anyone was about to notice.
Okay.
And so the research I did during my dissertation was, can we take a look at the behavior of the system internally and build a model of what it's doing without really understanding why it's doing anything? Can we take a look at what the pieces of the system are doing and notice patterns that, if they change, would lead us to believe that what the system is doing has changed. So the specific example I worked on was communication patterns between the components of an internet service. So you take a look at internet services are architected very, very nice for this type of thing. You've got components that have some high-level functional purpose. You've got, again, going back to the e-commerce example, you've got your shopping cart machines over here. There's a bunch of machines that are only for keeping track of all the items in people's shopping carts. Okay. There's another set of machines that is responsible for all the product catalog data. Mm-hmm. Another set of machines is responsible for recommendations or something like that. Mm-hmm. Now, when one of these groups of machines goes and talks to another group of machines, you think that's probably important. Mm-hmm. There's a reason why the shopping cart goes and talks to the product catalog every now and then, is so that it can show you the name of your product when you look at your shopping cart. Mm-hmm. And if you watch the system across enough users using the site and across all these operations, you'll see that when a particular type of request comes in, the shopping cart goes and talks to the product catalog. When the user comes in here, this component makes a call to that component, etc. Mm-hmm. And you don't know why it's doing these things, but you see it often enough that you'll believe that it really should happen. Every time someone comes in, this call happens. Mm-hmm. And if you model those properties, then whenever it changes, if all of a sudden someone comes in to look at their shopping cart and their shopping cart doesn't make a request back to the product catalog, or you notice that this is never happening anymore, all of a sudden it's stopped, then you don't know that it's a failure. It might just be a change. Maybe someone's changed the way the site works, but it's certainly worth alarming on and saying someone should double check that this is what's supposed to be going on.
Interesting. Mm-hmm. And this is all happening just via pattern analysis.
Yeah.
And not really caring about the details of the application. It's basically, you're looking from the bottom up to see what's happening.
Yes.
Essentially.
Yeah.
Very interesting. Does it require a large number of since you're dealing with statistics?
Yeah.
Does it require a large number of operations, a large number of nodes? Does that make your stuff easier to understand?
It does require a certain amount of workload coming into the system. I mean, you want to make sure that you're exercising all the different things that your site could be doing, so that you see all the options and kind of learn what all the different things look like. So, for example, if you were doing this to a brokerage site, you'd want to probably build one model of how things behave while the stock market is open, another on how things behave when the stock market is closed. Because the site is going to change its behavior quite drastically across those things. So you need to engineer some of those types of things in there and make sure you are representing both types of behavior. But it turns out that these internet services are so large that you basically don't have to fret the statistics about it very much. It's just the small mom and pops, you would have a hard time using the statistics there. But once you get to the point where you've got, I'd say, even tens of machines or certainly 100 machines running your site, you're going to have enough workload.
Interesting.
Yeah, that you'll see what's going on.
Now, what about a site like, without using names, although I could, I don't see why I couldn't, but for the sake of being PR friendly and not having to edit this interview. How about a site that allows people to basically upload video, upload podcasts, upload music, share stuff, create virtual playgrounds, etc., where you have millions of users with the capability to do a whole different number of things. That increases the complexity of what you have to solve, because you might not know or be able to know whether or not someone's uploading a podcast, which is the type of file, if you're not interested at all in the application. So that could be harder to figure out what's going on.
So I should mention, I guess, that one of the limitations of this, of detecting these problems by looking at how components are interacting with each other, is that you're limited by the granularity of the components that you're looking at. So, for example, if you're looking at a recommendation service or something, and it's recommending, you watch this podcast, maybe you'd like these other podcasts as well. As long as looking from the outside at this thing's behavior, not seeing what's going on inside, but just the fact that it's looking at the list of podcasts, it's going and looking at the user database and looking at their preferences and things like that. As long as it's doing those high-level things, you're not going to notice that there's a problem, even if it's giving you totally bad recommendations and just messing up. So you're not going to so you're not going to be able to tell problems like that. Now, if you have a situation where, for example, someone is uploading a bunch of of files, and you have like a file, whatever FTP side component or something, and then that goes and ships off files. Podcasts go over there, and whatever video goes over there for processing, and this thing goes over here. Now, even though you don't understand what these files are, you'll be able to say, in general, about 10% of my files go over to that component, 10% of the communication happens over there, the other 80% goes over there, and if there's any significant deviation in that, you can alarm on that as well. Now, that could change because of your user workload changing. You could have, all of a sudden, people decide podcasts aren't the big thing anymore, we only want to do video casts, and so you'll all of a sudden see your audio podcasts drop and your video podcasts go up, and then you'll alarm, and you'll have a false alarm at that point.
Interesting. So now, for example, Channel 9 is hosted on OrcsWeb, which they're a great internet hosting service for lots of different websites. And I get emails, or the dev team gets emails once in a while about something tripped an alarm. So they're already running sort of SMS or these types of applications where they're already doing this thing. But are you saying that those applications are a little more, they require a little more understanding up front?
So there's two things that those types of alarms do in general in practice right now. One of the things is they'll look at a specific machine and they'll take a look at these generic counters, like the CPU usage, and they'll throw an alarm when the usage has been really high, 100% for a minute or 5 minutes or whatever, some configurable threshold. So if the machine ever runs too hot, they'll say this might be a problem. And then there's also the types of alarms that will be thrown when the application itself writes something out to the error log. And so there you're depending on the person who wrote the application originally to say this is a bad situation, here's an error message, and then someone says, oh, there's an error message there, that's an alarm, notify dev team or something. But all these things end up working generally in either on a single box level or on the single box level, or based on something that's already been programmed into the system. And so what the type of things that I work on with this statistical distributed stuff is really, can you start to reason about the system as a whole in some way without requiring a lot of a priori knowledge about the architecture of the system, the structure of the system.
Excellent. I mean, that's a clear distinction between the two. I mean, I like that. I mean, it's good to force that issue home. You're talking about large-scale distributed computing.
Yeah.
And in the case of something that happens, say, on a Channel 9 site, say a node goes down, an email will come and say, we noticed that node 1 has been running at 100 CPU for 5 minutes.
And there's nothing wrong with that. I mean, so if you have a good understanding of your application, and you can put in these specific checks for things that you know are bad, you should go ahead and do that.
Sure.
Yeah. The challenge comes up with these large systems that change so frequently, and they have so many different ways that they could fail that you can't anticipate beforehand. I mean, if you imagine looking at how hard it is to write bug-free software. Now, this is bug-free software, and it's compounded by the fact that you have tens of thousands of machines, any of which they're going to have hardware problems occasionally. Plus, you have human operators running around and plugging in new machines and sometimes making mistakes, or putting out a patch when they shouldn't have put out a patch, and human error as well. Plus, then the regular software bug fixes. So you're always going to have things that you didn't anticipate going wrong. And because the system is changing so frequently, you also don't have the time necessarily to keep track of all of the stuff that you have to keep track of if you were going to do explicit detection of all these other problems.
Sure. So it's sort of like I'm sure you've heard of Anders Vinberg. He's an architect in the team that does SMS and all that other great management stuff.
Yeah.
His notion of isness and oughtness. So basically, you're talking about that on a distributed scale where oughtness is this sort of patterns that you're recognizing. Okay, this is normal.
Yeah. And
then isness is okay. This is what it is. And then basically you do statistical analysis on the two to figure out what's off.
Yes.
Right?
So if we wanted to talk about this isness and oughtness stuff in terms of the statistical things, it's basically you're taking a look at what is, and then from that taking some very simple assumptions that you hope are going to hold in this large-scale system, and using that to derive your notion of oughtness. So your oughtness ends up being a higher level of rule. So, for example, rather than saying this machine ought to talk to this machine over here whenever this request comes in, you instead measure, and you have your higher level oughtness that says, I'm going to assume that most of the machines are behaving correctly most of the time. And so therefore, if I see something happen most of the time on most of the machines, I'm going to believe that that's what ought to be happening. And all the corner cases where that isn't happening, that ought not to be happening.
Okay.
And so it's a very simple assumption. Most of the system is working most of the time. Okay. And any anomalies that show up, those are bad. But it doesn't require you to understand beforehand what exactly ought to be happening.
Interesting. Unless you start to analyze a very chaotic system, in which case it's going to be very difficult for you to figure out what's supposed to be happening. Now, arguably, a system like that could be useful. I mean, some sort of, as I was saying, distributed mechanism that does all kinds of random things.
Yeah. So luckily, web services today are still simple enough in terms of functionality. I mean, they're nowhere near the number of features that you see in Word, for example, or most desktop applications actually. And so that type of complexity in the number of features that could be interacting and chaos that could be going on gets drowned out by the fact that you have millions of people using it every day, and so you see all the combinations of things going on. But yeah, if at some point web services, features that they provide get so complicated that no one ever uses them, then yeah, that would become maybe rather chaotic and difficult to deal with.
Absolutely.
Yeah.
So let's move a little bit away from a distributed system, because in a sense, an operating system is a distributed system of components. It just happens to live in one place.
Yeah.
And there's no need for an internet connection. It's still a distributed local system with all kinds of interacting components, dependencies, blah, blah, blah.
Uh-huh.
So you could take the same sort of analysis that you do and apply that to what's happening in a local system and understand what could be causing this local system to not be behaving like it should. So bring the reliability issue back to the local machine, which still we have work to do in that area, clearly. But don't get me wrong, I mean, XP is getting better, Vista rocks, it's getting better and better, blah, 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 but...
Now, there are some challenges to using it that way, because you lose some of the advantage of the law of large numbers when you move down to a single system, running a single workload. Okay. So if you have... so let's say you've got your operating system, and you've always been a serious guy. You're running all sorts of Office applications and stuff like that, and you've done your pattern recognition to see what's normal. You run this application, and something talks to disk, something talks to memory, something talks to the network driver, and stuff like that. Now all of a sudden you decide to take a break and you install a game onto your system, and all this pattern recognition that you've done in terms of what's supposed to talk to what goes out the window when something talks to the sound driver or the 3D graphics engine. And now if you were able to collect all these observations of what's being done on your system across everyone running this operating system, then you would be able to learn the patterns of, okay, some programs act like games and they talk to these other devices. Some programs act like this and they talk to these other device drivers, and they have different patterns of behavior. But you would need to start finding a different way to get those observations so you could take advantage of this law of large numbers and getting the workload observations that you would need to do to infer the right patterns.
Absolutely. And that's important, because it's the same thing with computer vision, it's the same thing with machine learning, right? You need numbers.
Yes.
You need numbers. It's the fact, and it makes sense because it's statistics, right? You're running basically a statistical algorithm or a group of them.
Exactly, yeah.
And you need to have lots of numbers. It would just be interesting in the sense that at any given time, an operating system has thousands of processes running. And millions of things going on.
Sure. So
it would just be kind of interesting to say, all right, this one guy's computer, he's a developer, he was always running Visual Studio, he also runs Office because he works for Microsoft and is also always checking his email, or her email, and likes to play games after hours or whatever.
Yeah.
But there's this one application that keeps causing this problem when this other thing is happening at the same time. I understand it's an unbelievably complicated problem that you're running into, but if you were to run a tool like you've created on a machine for a year, but one person uses it, you'd know a heck of a lot about how that person uses that one computer.
Oh, yeah.
So you could run some sort of interesting analysis when I go to do something, and it's like, ooh, that's not going to work because... Whatever, I hear you.
Yeah.
I always bring everything back to the OS because that's my favorite thing.
Well, there's a lot of stuff going on.
But let's talk about what are some of the big challenges for you? Let's talk about that. What are some of the things you mentioned a little bit where it's not going to work if you don't really have any idea what's going on? Sort of, I think that's what you said.
Yeah.
Or the type of site. So give me another example of the challenges you're facing.
Well, I'll tell you a bit about one of the things I'm working on now.
Sure.
And so, so I told you about the work I did in my thesis and stuff back when I was at Stanford, and that was really focused on what's going on inside the internet service, inside the data center, and how all these components are interacting with each other. Since then, now, more recently, I've started working on, from the internet services point of view, the content provider's point of view, what are all the other things that can get in the way of the user of the site having a good experience or good reliability talking to the site. And so yeah, you definitely need to make sure that your data center is up and running and that all the computers there are going. But it also it turns out that these content providers they also care about the reliability of the internet. So you've got this customer who's trying to reach you. If any network is down between you and them, and if the internet isn't routing around it like it should or something, then that customer can't reach you. And it turns out that this is a problem because many customers, I mean, the network itself is generally not, it's not in people's face. They don't blame the network right away. They'll blame the site. Yeah, I couldn't get to this site. I can get to that other site. Why can't I get to this one? It's their fault.
Good point.
The second one is obviously financial as well. You can't show advertising, you can't sell stuff, you can't make money if people can't get to your site. And so the work I've been doing recently has been on looking outside of the data center. What data can a content provider get about the internet in order to help debug and resolve problems out there in other people's domains, in order to make sure that their customers have a good experience.
Interesting.
So we've been looking at data from one side of MSN, collecting basically everyone's records of everyone's HTTP requests to that site. No privacy information or anything like that. Just a request came in and it succeeded, or it reached MSN or it didn't.
Got it.
And we're collecting this information out of proxies, and then at like content distribution network proxies, and then we correlate those successes and failures to a network topology, and then we can say, this ISP over there having a hard time. Every day, 8 a.m. for 5 minutes, goes down.
Interesting.
Comes back up. And you can then detect these failures. Operations can use this information to prioritize who they need to talk to and what they need to drill down further into, and then help people realize that there's something going wrong and help them fix it.
Excellent. That's really an interesting point to extend this out to the internet, which really is very chaotic.
Yeah. The nice thing is that detecting problems is also much easier. You're able to reach them, or you weren't able to reach them. There's not. You don't have to worry about, was I supposed to reach them?
Exactly.
If you're trying to reach
ought
them,
I reach them or ought not I reach them?
Exactly.
Interesting. So, if I'm on the same machine and I navigate to site A and I get there, but I navigate to site B and I can't get to it, what you're saying is that actually could be an internet problem with some pipeline that specific place is using.
Yeah.
And not a problem with the internet, as most people think of the internet as like, I'm online, the internet.
Yeah.
So it's composed of all these very different sub components.
It's really it definitely is, and the internet is not just always on or off, right? So it's quite frequently happens that I can talk to I can make a connection to some computer over on the East Coast, and I can make a connection over to some computer down in California, but those two computers can't reach each other, even though I can reach both. And so this is actually one of the reasons why products like content distribution networks and stuff, they actually sell services that say, if anyone tries to reach your site, send it to me first, and then I'll route the query around appropriately and find the best way to reach it through my own kind of network on top of the internet.
Interesting.
I know who can. Let's see, how would you say it? You can tell I don't sell these products.
Yeah.
So, let's say you have a content distribution network, like a peer-to-peer overlay over the internet, and one, you get your request to one of these guys. This guy then asks its friends around the country, says, which one of you can reach this end site fastest? I'm going to send this request off to you to forward on to them, because I can't reach them right now. And it turns out that improves your reliability quite a bit.
Absolutely. It's classic peer-to-peer, which I was just going to ask you that, actually, is how this kind of tool could work in a true peer-to-peer network of various nodes. And let's say we're doing a BitTorrent download, which people do for whatever. It's an interesting technology. would there be a way to manage and figure out what node had a problem with what piece, or why the file isn't getting down in my machine through this network? I don't really understand very well how that works. So this would be a good example of if I were your program. I have really not. I don't have a good understanding of it. Well,
that brings up an interesting challenge that I haven't thought too much about, and that is that you've got this distributed system, but all your analysis of your observations, the question is who's doing the observing. So if you're really in a distributed environment that really is totally peer-to-peer, and you have to ask, who is the person who's going to be doing the analysis of this data, and where are all these observations going to go? Who's going to do the analysis of this data? If you're doing a BitTorrent thing, then I guess the person who would want to analyze this data would either be the person who originally put the file up there. Let's say someone's trying to sell something over BitTorrent or something like BitTorrent where you could charge for things, or it's the person trying to download the data. And in that case, then in both of these cases, then the question is, why is this peer-to-peer network going to trust this one person, and send them the observations of what they're doing from this machine? Why would you bother spending your bandwidth not only to, serve out these BitTorrent files, but also report back observations to anyone about what you're doing? What's to keep the Motion Picture Association from saying, I want to see what everyone is doing because I want to debug you guys. And then of course I don't think people would go with that.
Of course not. Well, they shouldn't be doing that stuff anyway. But, it's still interesting. If it was maybe BitTorrent in the way that it's used. I mean, BitTorrent wasn't necessarily designed to steal movies from Hollywood.
Oh no.
But
let's say everyone's downloading Linux CDs.
Okay.
Then maybe people would trust Red Hat or so and say, I'll let Red Hat know what's going on, and then maybe if there's something going wrong, some bytes are getting corrupted regularly, Red Hat could debug it and put out a patch for BitTorrent. That would be. But you do have that trust issue there, where you have to you'd have to convince the nodes that they should be reporting this data back.
Excellent.
Or you have to find a totally different way of doing it, some sort of distributed statistical analysis, which would be another challenge.
PhD for you.
For someone else.
So let's talk, part of Channel 9, I sometimes get too caught up in the technology.
But
it's also about the person, right? So you seem like a young man, graduated from Stanford. I mean, that's an incredible computer science school. So you're clearly a great student, talented individual. And you decide to come to Microsoft. Why did you make that decision? Being down in Silicon Valley. Just curious. I mean, we have an incredible research, but what does the Microsoft research look like to the outside world? Like, people want to come work here.
Oh yeah. So I mean, the people who are here are great. I think I'm very lucky to get to work with everyone here, and so that's just obviously a huge draw. You said it yourself. The other reason that I wanted to come here was I did want to stay in research and kind of doing an academic type of thing where I find interesting problems that I think are fun, work on them, publish papers, tell people about it, that type of thing. And there aren't that many great places left to do that. The other advantage of being at MSR specifically, as opposed to say doing research in a university or something, is that Microsoft has these large-scale systems that they're trying to manage and build up and everything, and so it's a really great opportunity to get data from those systems to then analyze and use in the research. If you go to a university environment, when I was at Stanford, it was very hard to get data from any real system. I worked with, I spent a couple of years working with one internet service to do that. I mean, they were great. I really appreciate everything they did, but it's not as easy as getting data once you're actually inside. That's for sure.
Sure.
Yeah.
Okay. Excellent. So you're going to stick on this path for research
for a while until something more fun comes up. But I'm certainly having a lot of fun right now.
Cool. And of course, it's nice also to know that perhaps some of your research will end up in a product one day. that millions of people will rely on and use, which is kind of unique also for MSR.
It is having a real world impact with the work that one does is very
cool.
Yeah.
Excellent. So what else? Did we miss any of the problem space? Did we tackle all the things we needed to tackle?
Well, I don't know that I know what the whole problem space is. So I'm sure
well, you're not supposed to.
No.
Because the idea is you don't know what the problem space is. You have to figure it out by pattern analysis.
Ah, yeah.
Right?
Yep.
Excellent.
Yeah.
This was very cool stuff.
Thank you.
So, I guess we have pretty much covered. I'd like to always talk a little bit about how things work, right?
Sure.
Basically, we've covered why you do it.
Yeah.
We covered how, right? The how is I do statistical analysis, and I don't really know what's going on, but I think it should work this way, but it's not. So I can throw an alert. It's much more complicated than that, obviously. But let's talk a little bit more about what, I guess, or like what exactly is going on here, what you can talk about. I mean, you say your dissertation is public knowledge.
Yeah.
So what exactly? Let's construct what this thing is that you're talking. This distributed analysis machine. What exactly is it?
So the first piece is really an instrumentation layer, and this, there's a lot of folks who do this instrumentation. I think it's pretty standard stuff. You just go in, and whenever a request comes into a machine, you make a record and say, okay, here's a new request. I'll give it some ID number. It just entered, the front end web server, and write out a log to disk or somewhere saying that this thing happened. Then you need to make sure that whenever this request then gets sent off, or you do some work on behalf of this request that then sends off a request to another machine, you'll tag it and you'll say, this next request, it also has this unique ID. I'm doing this work because of that thing over there, that original thing over there. And now what you do is, now every machine in your distributed system ends up having a collection of stuff that says, I did something, this request sent me, I got a request over there to do something, and it had a work ID of 120. And then you'll go through and you'll say, then I went ahead and talked to that guy and told him to do something because of work ID number 120.
Okay.
And you'll get all this data, all these logs about what's going on. Now you'll gather all these things and you'll now sort them, and you'll say, okay, give me everything that had anything to do with work ID number 120, and you'll get a big long list of everything that any machine did to deal with this.
Okay.
And so now you'll get your path that this request ended up taking through the whole system, and you'll then try to build up your knowledge of what do each of these paths look like. And there's various ways to do this. The way I used was just you build up a probabilistic kind of grammar to describe what this string looks like. So you'll say, half the time whenever you see this type of machine doing this type of task, then the next one, half the time the next event that you'll see is something from that machine doing something over there. The other half the time you'll see something from that machine doing something over there. And you build up this grammar now, and then now whenever you get any new request path, you can compare it to your grammar and say, does this look like something that's probable given the kind of language I've learned so far?
Interesting. So, I mean, in essence, it really is machine learning.
Yeah.
I mean, it relies on the same math.
Yeah. So I'm not a machine learning person, but I borrow their algorithms and work with people over there in the other building.
Cool.
Whenever I can.
Yeah, I was just over MSR Cambridge interviewing Tim Harris and Simon Peyton-Jones, who work on the software transactional memory. And I got a tour through Christopher M. Bishop's group. He's the machine learning guru over there. And one of the guys we met, I think his name is Tom Dinka, is like the algorithm dude for MSR Cambridge. And he came up with the expectation propagation algorithm that's heavily used in gaming algorithms and etc. But I just brought that up because they're all, many of them are young, like you are, and it's a very interesting. There's some very interesting research over in Cambridge.
Yes.
This is where the machine learning group really is headed.
There's some very good machine learning folks in Cambridge.
Certainly. So it's just it's interesting. I like to try to put the pieces together of what people are working on. And so some people use machine learning and pattern recognition for computer vision, like Andrew Davis and team, and you're using it
for systems management. Yeah, that's one of the fun things. That it's so easy to get data, large amounts of data, for these systems. It's very thin scale than a lot of machine learning problems. There's some, if you want to do handwriting recognition, you have to work hard at getting a lot of people to handwrite stuff for you.
True.
If you're doing computer vision, you have a little bit of an easier time. There's photos all over the place now. But oftentimes, getting data is difficult. And that's not the challenge in systems.
Yeah, you have
that's for sure.
Plethora of data.
Yes.
Fantastic.
Drowning in information.
Very cool.
Yeah.
Well, this is awesome. It's great to meet you.
It was great to meet you.
Thank you for your time.
Thank you.
And good luck with your research.
Thanks.
Hope you hang out at Microsoft for a while. At least get a few papers under your belt.
Oh, I'm sure. I'm enjoying it here a lot.
Excellent. Cool.
Beautiful.
So you hear that, PhD Stanford people? Check out MSR. Sorry, shameless plug. This is my favorite group in the company, besides Windows. All right, man.
Okay.
Take care.
You too.